Hello everyone, welcome to this lecture. In today's lecture, we will extend our discussion on the concept of process synthesis, and we will look at some further details how we can use this concept to for the generation of alternating flowsheet structures and perform some basic economic evaluation. So by end of this lecture, you should be able to grasp the fundamental concepts and principles of chemical process design and the associated challenges involved in decision making. You should be also able to analyze, create, and interpret the reaction separation recycle flow sheets. And you should also be able to understand the role of each component in the process and how they interact to achieve the desired chemical transformation. You should be able to understand what is a gross margin of a chemical process and how to consider cost, revenue, and other financial factors to evaluate the profitability of a chemical process. In this section of this chapter 1, we will look at the process of generating alternative flowsheet structures. This section is broken down into 7 subsections, as you can see on the screen. And in the next few slides, we will look at the details of all these subsections. Here we look at the detail of what is a process concept. So the process concept is a very basic idea, so basic that it doesn't achieve much. But it is the first step in developing ideas about what will happen in the process. Okay, and here we look at what are the desired products, and actually to achieve those desired products, what are the feedstocks and what are the reaction pathways that lead to those products. Okay, so to look at this process concept, normally what we do is that we start with a very basic idea. Like here, for example, you can see this a cloud or a blob, and inside this cloud or blob, in the middle, here you have the reactions or the stoichiometric of these reactions, capturing the reaction pathway that is being considered. Okay, and feeding the cloud are the reactants that are going to take part, or your feedstock, and then through this reaction pathway, these reactants will lead us to the desired product. Okay. I have also put here to show you that the reactants are also leaving this blob, because all the reactants might not be consumed in the reaction, so they are the unreacted reactants that you might want to recycle to the mainstream. Okay, so as you can see that this is a very basic idea of what we want to achieve, what we need for it to achieve. Like we need the reactants and the reaction pathway. Okay, so this basic representation is what we call process concept. Then the next step to this process is developing an input-output structure of the flow sheet. And what we do here is that we look at the similar detail, but now we add more information here. So it's an extra layer of information on top of our process concept. Again, here we are looking at what is the feed to this block or this blob that we had in the previous slide. But here we are now considering it with rigid boundaries. Okay, and then we again looking at our product. And in addition to our reactants and products and reaction pathway, we also start thinking about recycling of the material and removing some unreacted material and impurities. Okay, so as I said, it's an extra layer of information on top of our process concept. So from this input-output structure, we can construct our first flow sheet structure, that what we call block flow diagram. And as I said in my first lecture, that these are basic diagrams that we use to provide a bigger picture of our process, where we look at different processing steps without going into the detail what and how we are going to achieve that step. Okay, so here, for example, you have raw materials entering the reactor, then we have some product with unreacted material. We feed it into separator. Maybe we need to increase or decrease the temperature of this feed stream. And then we choose to recycle or not recycle depending on our process. And finally, we discharge the unreacted material or waste into the environment. Okay, so this is a very basic structure here. But depending on your system, you might want to add more details. For example, you might want to add a feed preparation step because you might have to raise the temperature, pressure, or phase, or change the phase of your reactants before you feed into the reactor. The reactor itself can be a series of reactors or can be different technologies. For example, similarly, various technologies available for separation, distillation, membranes, absorption. We can decide about recycle based on if it is going to be beneficial for our process and also on our economic evaluation. And finally, you might want to add some environmental control because obviously we cannot just vent our waste streams into the environment. We have environmental laws for that. We cannot emit, for example, carcinogenic materials into the environment. So we might have to actually treat that waste stream before we can actually discharge to the environment. Okay. So depending on your process, you can add more detail or more blocks into this block flow diagram. So knowing the input-output structure, a very basic idealized material balance can be carried out. We can estimate the gross margin for an assumed yield and making other simplifying assumptions. For example, we can assume that we have a full recovery of reactants or we have 100% conversion. And but we still don't have enough information to make detailed evaluation in terms of we don't have the operating cost, we don't have the capital cost. So this very initial evaluation just look at with very simple assumptions if the process is going to be profitable or not, depending on what are the purchasing cost of reactants and what is the selling cost of the product. Okay, so very basic gross margin valuation. Now to help you understand what is gross margin and how it can help us make go no go decision on our process, let's look at this example of cumene synthesis process. And here we are only considering the primary reaction. Okay, so if you look at your case study of cumene production, there are two reactions. So here we are only looking at the main reaction for the synthesis of cumene, that is benzene reacting with propene to form cumene. Okay, and the graph here, all these graphs, they are the cost estimates of these chemicals over a time period, and these are generated by ICIS Chemical Business. So they regularly publish these price of these different chemicals, okay, over time. So let's evaluate the economic performance in, let's say, June and December. And here you can read the prices of these different chemicals. For example, here you have benzene, cumene, and propylene. You can read their prices in dollars per ton. Sometimes you might have different units, for example, dollars per barrel. So you just have to use those units or convert them. But here we have dollars per ton. And a key take-home point from this slide and the next one is that the prices are volatile, and therefore the economic performance of a process operating in these conditions is also volatile. Okay, and that is why normally when you are designing a process, we not only look for 1 year price timeline, we actually look at several years of past predictions as well. So here we calculate the gross margin per kilomole of cumene produced, okay, and the stoichiometry is simple. We have 1 mole of benzene reacts with 1 mole of propene to form 1 mole of cumene. So first we need to calculate the price in dollar per kilomole using the molar mass information. Like for example, we have here, and then we have the cost of dollar per kg from these graphs. Okay, so we can calculate dollar per kilomole. Then to calculate the gross margin, we need to take the difference between the revenue earned from selling the cumene and then the cost of purchasing, for example, benzene and propylene here. So if we look at for 2017, we can see that the gross margin is 0. And that's obviously not a good news, as we have assumed 100% conversion already and 100% recovery. That is, in most cases, would not be true. And have ignored all the costs, operating costs, capital cost, other than the cost of the reactants. Okay. So now let's look at December 2017, if there is a good news there or not. So the reactants are both more expensive in December, okay, but the product is also more valuable. So in this case, the gross margin is around $3 per kilomole, okay. So that is good because we have a positive gross margin, but we don't have enough information to judge whether the process will indeed be economically viable at these economic conditions. Okay, so this is still too early to decide if this is a techno-economical process or not. But just by this very simple information, we can decide that if the process is a go or not go. For example, if we look at this situation here, if it is 0 or if it is in negative based on last few years of your data, then definitely that is no go process. But if it is showing even a smaller positive trend, then we can actually further investigate and see if it is still economical or not.